This is Radhika. I am going to discuss about the power electronics devices. In this topic, we are going to discuss about the SCR commutation. Under that, today we are going to discuss about the class A commutation. So here, in this, main topics are thyristor commutation, different commutation techniques, and circuit and working of commutation techniques. So actually, what is the thyristor commutation and these techniques? Actually, first of all, what is the commutation? In electrical engineering, the term commutation means that the transfer of current from one path to another path. But in case of power electronics, it refers to the process of turn off of the thyristor or semiconductor device. In normally, the commutation means the current flowing from one circuit to another circuit. But in case of power electronics, it means the process of the off position of the thyristors. When we want to off the thyristor, we can apply the commutation. In these modern days, it is very necessary in some of the applications of power electronics devices or circuits to turn on as well as turn off of thyristor at a required instant of time to achieve high degree of accuracy. A thyristor is turned on by applying a signal to its gate cathode circuit is very convenient method. So turn off of thyristor is not possible very easy as in case of turn on method, but it requires special circuits. For turn off condition, it needs the special circuit, but to turn off the thyristor, we can use the commutation. So in this, a thyristor is turned on by applying signal to its gate cathode circuit. For the purpose of power control or power conditioning, a thyristor must be turned off as desired. The turn off of a thyristor means bringing the device from forward conduction state to forward blocking state. So here, in this, the thyristor turn off requires that its anode current falls below the holding currents and a reverse voltage is applied to thyristor for a sufficient time to enable it to recover to blocking state. So here, actually, what is the commutation? What are the conditions for commutation? The commutation is defined as the process of the turned off of a thyristor. Once thyristor starts conducting, gate losses control over the device. Therefore, external means may have to be adopted to commutate the thyristor. So here, and also several commutation techniques have been developed with the sole objective of reducing the turn off. Actually, to turn off the thyristors, we have the many types of turn offs. In turn offs means it is the commutation. The classification of commutation techniques is based on the manner in which anode current is reduced to zero and in the configuration of commutating circuits. So here the thyristor commutation techniques are resonant LCR underdamped RLC circuits to force the current and or voltage of a thyristor to zero to turn off the device. So normally we can using the circuits of LCR RLC circuits to force the current and voltage of the thyristor. It goes to 0 point, mean that time it will be goes to turn off. Actually, the types of commutation techniques are class A, class B, class C, class D and class E. Class F commutation. The class A commutation will discuss about the load commutation. Class B commutation discussed about the resonant pulse commutation. Class C commutation discussed about the complementary commutation. Class D commutator the impulse commutation, and class E commutation is the external pulse commutation, and class F commutation for the line commutation. So these are the commutations. Before going to discussion about class A commutation, we can watch the one YouTube video about the commutation.
We have discussed turning on methods of SCR. Now in this video we are going to see commutation methods of SCR. Commutation method are nothing but turning off of an SCR. Now what are the different types of methods or different type of circuits can be used to turn off an SCR, or SCR itself can be turned off as it is own, that we are going to see in this video. So basically, first of all, we have discussed some advantages and disadvantages of SCR. If you remember, we have an advantage of SCR is that turning on of a SCR is a very easy method, but turning off of an SCR is a difficult method, because once it is latched into on state, it is difficult to bring into the blocking state, or you can say off state. So what can be done to switch off the SCR? Because SCR is nothing but switch. We are going to use SCR as a switch, and if it is used for the switching application, it should be turned on and it should be turned off by the time required. So we'll see how it can be turned off. So first of all, the commutation is the process of turning off a conducting SCR is known as a commutation. When it is turned on, we say that SCR is a latched, and IL is important at that time while latching the SCR. When we have discussed VI characteristics, I have told you that latching current is an important parameter while deciding turning on of a SCR. But the holding current is an important parameter when you are understanding the turning off process of an SCR. Now, depending on the nature of the source, it can be AC or DC. The commutation can be natural or forced. So first we are going to see how naturally SCR can be turned off, and if not, what can be done to forcibly turn off the conducting SCR. So different techniques, commutation techniques are: first is a natural commutation and forced commutation. Your source can be either AC or it can be DC. If your source is a AC source, it is known as a natural commutation. We have discussed what is natural commutation in the previous video, but we are going to see it again. We have discussed some part of it, how current can come to the 0 point naturally. That is what we wanted. If we want SCR to be turned off, what is required is that anode to cathode current should be 0, or it should be below holding current. Once your current comes to the below holding current, your SCR can be turned off. That is the requirement to turn off the SCR. So with the AC source, it is a natural commutation. Natural commutation, that means you don't require any external circuitry or any external device to turn off the SCR. SCR as it is will turn off at one particular point. Forced commutation, whenever we are using a DC source, that time it is difficult to turn off the SCR. So we have to go for the forced commutation. That means forcibly by using external device or external circuit, you are turning off the SCR. So this mechanism can be either current commutation or this can be a voltage commutation. So this current and voltage is nothing but, if you reduce the anode to cathode current below holding current, your SCR will be turned off. This is the first criteria which is to be satisfied to turn off the SCR. Second criteria is that if you provide negative voltage, that is voltage across anode to cathode, if VAK is reversed bias, or it is a negative voltage, then your SCR will be turned off. Now let's see. So here first we are going to discuss natural commutation. So natural commutation, I have shown a simple diagram. So this is my SCR, correct, and the load connected is a resistive load, and the source apply is a AC source. Whenever there is a AC source connected to the SCR can be commutated naturally. Now when it comes as a AC source, I have, this is my input voltage supply, this is my AC source given to the circuitry, and the load resistance, load is a resistive load. Here in this circuit, the current flowing through SCR is same as the current flowing through resistor. Now let's see, this is my input voltage which is given to the circuit, that is Vm sin omega t. So the amplitude for this positive will be plus Vm, and amplitude of this negative cycle will be minus Vm. And here I have shown the output voltage and the current flowing through the circuit, that is I0. So this dotted line is the I0, and V0 is nothing but the voltage across the resistive load. Now here for a positive cycle, that is from 0 to pi, when it is a positive half cycle, my SCR, this terminal is a anode, this terminal is a cathode, and this terminal is a gate terminal. Now here I have considered that my gate terminal is open. At this point, my anode to cathode voltage will be positive. Now I am providing positive half cycle. In positive half cycle, this point will be connected to the positive terminal of the battery, and this point is connected to the negative. That means anode is made positive with respect to cathode. Due to this, my SCR is in a forward blocking mode. Now whatever is the voltage across SCR, the same voltage will appear across the resistive load, because resistor is connected in series with SCR. Voltage across resistor will be similar as a voltage across the SCR. Similarly, current flowing through the resistor R is also the similar as current flowing through SCR. Now if voltage across SCR will be the positive Vm for a positive half cycle, so my output voltage V0 across resistance will also be the positive Vm. Now at the same time, current flowing through this SCR and resistor is same, so this is, I have shown the current flowing through with a dotted line. Now if you see carefully, as we have discussed in an earlier video, when the voltage given to the circuit is reached to the 0 point, my current will naturally also reach to the 0 point, because for a positive half cycle, SCR will be forward bias, and for a negative half cycle, SCR will be reversed bias. When a voltage is maximum, output voltage and output current is also maximum. When input voltage reaches to 0, output voltage also reaches to 0, as well as output current will also reaches to 0. While negative half cycle, SCR will be reversed bias. If SCR is a reversed bias, there will be no flow of a current through the circuit. If there is a no flow of current through the circuit, there will be no current flow through the resistor. So here the current and output voltage will be 0. So here if current is reduced to 0, that means it is automatically coming below holding current. And if my current is automatically coming below holding current, then my SCR is taking a transition from forward conducting state to forward blocking state. That means it is taking a transition from on state to off state. Because of this circuitry and this diagram, you can clearly understand that this is a natural commutation, because without using external circuitry, my SCR can be turned off if the forward current is reduced to below holding current. That is how natural commutation takes place. Now when it comes to the forced commutation, now forced commutation can be either a voltage commutation or the current commutation. Only difference, now when it comes to the current commutation, it is same as a natural commutation, but here you have to bring your current below holding current by using the external circuit. In natural commutation method, we are not using external circuit, but in a force commutation, you should have an external circuit which will forcibly bring your current below holding current. So let's see what is current commutation. If SCR is turned off by reducing its anode current below the holding current value, then the commutation is called as a current commutation. That means you should have a circuit which can be connected to the anode to cathode terminal or anode terminal and forcibly provide the reverse current or the negative current. If you provide the negative current, your current through the anode to cathode will automatically bring to the below holding value and your SCR will be turned off. Similarly, voltage commutation, if conducting SCR is turned off by applying a large reverse voltage across it, then the commutation is called as a voltage commutation. I'll explain you with diagram. So in current commutation, so if this is the symbol of SCR having a gate terminal, anode and cathode, you have to provide negative current to the anode terminal so that your IA, that is a forward current, will be reduced below holding current and then your SCR will be turned off. Whereas in voltage commutation, if you bring VAK, that is a voltage across anode to cathode, to the reverse voltage, or we can say you can use the external circuitry which will provide the negative voltage, that is negative VAK, then it will become a reversed bias. If it will become a negative and positive, then it will become reversed bias and it will automatically come in a off state. So these are the two methods, but this both the phenomenon should be take place by using the external device. So you are using the external device, it is also known as a force commutation. So I hope you have understood what is a natural commutation.
So this is the about the commutation. Now we are going to discuss about the class A commutation. Class A commutation or load commutation. It also called class A commutation and load commutation. So here in load commutation, for load commutation of a thyristor, the commutation components L and C are connected as shown. So this is the figure of the commutation, and this method is also known as resonant commutation or self commutation. Class A commutation or load commutation or resonant commutation or self commutation, both are the same. In this method, L and C components are used in series with the load resistance R. For low values of R, means in this is the diagram for class A commutation or load commutation. So in this method, for low values of R, the components L and C, are connected in series with R. For high values of R, the load resistor R is connected across C. So in this diagram, we have seen L, C and R connections. So it is necessary to that circuit must be a damper circuit. And in this method, of commutation, the anode current of the thyristor is the anode current of the thyristor is reduced below the holding current when these circuits, normally these circuits shows in this diagram, and it will be energized from DC source, respective current waveforms. From the waveforms, it is observed that the device current I rises to the maximum value at and then declines to 0 at the point. Beyond the point it tends to reverse and hence the thyristor is turn off. So here this diagram is the connection of the RLC C and L in series, and that will be R will be connected to parallel to capacitor. In the circuit, R is the load resistance for low value of R, L and C are connected in series with R. In this figure, for high value of R load, R is connected across C as shown in the figure. The essential requirement for both the circuits is that the overall circuit must be underdamped. Actually, what is the working of class A? When these circuits are energized from DC, current waveforms are shown on the right side of the circuit. It is seen that current first rises to maximum value and then begins to fall. When current decays to 0 and tends to reverse, thyristor T is turned off on its own at a constant A. And now class A commutation we can watch in YouTube video.
Is forced commutation and second category is natural commutation. Natural commutation is even in this session. So to understand class A commutation, these are my session outlines, where first I'll discuss basics of commutations. Then after we will see classification of commutation, and out of that classification of thyristor. So basically in power electronics we use high power devices, and those high power devices are a bit difficult to turn off. So in power electronics we use commutation process to turn off thyristor. And to get desired output in given power electronic circuit, turning off operation of SCR should be precisely timed. And as if you time it precisely, in that case one can have better efficiency of circuit and proper operation can be achieved. So commutation is a method by which we turn off SCR. Turning on process can be done by gate pulse, but turning off process cannot be done by direct switch, and for that we need to do commutation. So when we talk about commutation, so that is a process of turning off SCR. There are basically two categories. One category is forced commutation and second category is natural commutation. Natural commutation is even referred as line commutation. Now see, these two categories that is been done based on supply used. So here in forced commutation we use DC supply, and in natural or line commutation we have AC supply. Now when we talk about forced commutation, so in forced commutation there are total 4 different categories: class A, class B, class C, class D commutations. I will make separate session for all different commutations. So here I am just giving name, where class A commutation is even referred as load commutation. Meaning of it is it commute SCR or thyristor by load. So how it will do that we will see it in detail. And in natural commutation there is one category, that is class F commutation. So here commutation category with class A, that we will be observing in detail. So let us try to understand first basics of class A commutation. So that is even referred as load commutation. Why? The reason is load will turn off SCR in this category. So it is even referred as load commutation. In its working, you will get to know like how load can turn off SCR. Here, commutation of SCR is done by load current. So first of all, let us see the circuit which is there with class A commutation. So when we talk about circuit, here we have supply Vs and this is DC supply. So plus and minus voltage, DC voltage that we are connecting over here, and that is what we are connecting it with this SCR. So you can see connection is given like this, and at load we have RLC circuit. So this is inductor, resistor and capacitor series connection that I have connected. So in this class A commutation, you will be observing this R, that is load resistance, and this L and C, these are commutating elements of SCR. So this inductor and capacitor is used to turn off SCR. Now how these elements are turning off SCR, so that thing that we will see it in complete detail step by step. So let us try to understand how it works. So basically you can observe this is SCR connected like this, as I have told you, and once you give gate pulse, so by giving IG means gate pulse, this SCR will get turned on, and this as this SCR is getting turned on, current will flow in this loop. So if I say I0 current that is flowing in this loop, so here first I will do mathematical analysis which explains you how current will flow inside and how many parameters that we need to focus about. So as if this current is flowing in this loop, if we apply Laplace transform, then we can identify this I0 current, and that I0 current will be voltage divided by impedance. Now here voltage will be Vs divided by S in Laplace transform, and this impedance will be Ls in series with R in series with 1 by Sc. So inductor in Laplace will be L into S, resistance in Laplace will be R, and capacitor in Laplace will be 1 by Sc. So from Laplace transform, output current will be I0 is equals to voltage divided by impedance. Voltage is Vs divided by S, and impedance is R plus Ls plus 1 by Sc, where R is R only, but inductor will changes to Ls and capacitor will be 1 by Sc. Now to understand this formula in second order differential equation, I am just doing bit adjustment, so we can rewrite this formula in this way, like see Vs by L, this divided by, now you can see second order equation that is there in denominator, that is S square plus R by L into S plus 1 by LC. So this denominator, that is what second order equation. So we can say this second order equation is characteristic equation for this class A commutation circuit. Now if you see standard second order characteristic equation, then standard characteristic second order characteristic equation is S square plus 2 zeta omega n S plus omega n square is equals to 0, where omega n is natural angular frequency, zeta is damping constant. And if we compare these two equations, you can say omega n, that is 1 by square root of LC, and 2 zeta omega n, that is equals to R by L. And if you simplify this, you will be finding omega n is equals to 1 by square root of LC, and zeta will get to R by 2 into square root of C by L. And that is what we can have it by substituting omega n in this term. And this term is what? 2 zeta omega n is equals to R by L. Where if you place omega n is equals to 1 by square root of LC, then you will get zeta is equals to R by 2 into square root of C by L. So now we have value of zeta and natural angular frequency. Now see, to understand stability, we need to have underdamped system. So for underdamped system, you will be observing this oscillation amplitude will decrease with respect to time. Then one can say this system is stable. And here this LC oscillation, that is underdamped system that we are considering. Now for underdamped system, as we know, this value of zeta that should be less than 1. So as if you consider this value of zeta less than 1 for underdamped system, we can say this term is less than 1. So as this term is less than 1, we can have condition for stability with underdamped system, and that condition is R square should be less than 4L by C. So if you choose RLC as this relationship, then we can have underdamped system, and that underdamped system will turn off this SCR. Now see how. You can see over here this is positive cycle, and during this positive cycle this SCR will be in forward bias. So we can say as if we give gate pulse during forward bias, this SCR may get turned on. Right now you can observe this oscillation without this SCR. So if you just connect VS supply like this type of underdamped oscillation will happen. But as if you give gate pulse, then only this SCR will get turned on. So as if SCR is getting turned on, it will remain turned on during this positive up cycle. But once it reaches over here at pi angle, SCR will come in reverse bias, and as SCR comes in reverse bias, automatically it will get turned off, and that turning off operation that happens because of this LC oscillation. So let us try to understand how all those things are happening. So here resonant frequency for this, that will be omega r, and that omega r frequency for this underdamped system will be omega n into square root of 1 minus zeta square. And for underdamped case, this zeta will be less than 1. And to turn off SCR, anode current will go below holding current. So see, at this instant, anode current will go below holding current. This SCR will go in reverse bias after that, and then one can say SCR will be turned off. So here SCR can stay on during 0 to pi radian, or one can say during that time interval. You can see for this time interval only SCR can stay on. So if I say this SCR stays on for pi angle, 0 to pi angle, then we can say this T into omega r is equals to pi, where we can say this T is maximum conduction time of SCR, and that will be pi divided by omega n into square root of 1 minus zeta square. But as if you provide firing angle which is alpha, so if I fire this SCR somewhere over here with angle alpha, then this formula will changes to T is equals to pi minus alpha divided by omega n into square root of 1 minus zeta square. So that is how we can identify turn on time period of SCR. And turning off operation of this method is been getting done by load, which is made up of inductor and capacitor series connection. So that's why this commutation method is even referred as load commutation. Now let us try to understand all those things by waveforms. So here, as I have told you, circuit that you can see, this SCR is connected with L, R and C, where this R is load and L and C, that is commutating elements. And to understand this, I am showing you IG current over here, capacitor voltage over here, load current over here, and thyristor voltage VT over here. Now initially this SCR is off, and now to turn on this SCR we will be giving gate pulse. So once you give gate pulse, you can observe this SCR will get turned on, and as this SCR is getting turned on, you'll be observing this capacitor voltage that will get charges to Vs voltage. And as this capacitor is getting charges to Vs voltage, you will be observing load current that will flow through this anode, and that load current even will increase like this, right? And that will increase till capacitor is getting charge up to Vs voltage. And as this SCR is on, voltage across SCR will be 0. Now, once capacitor voltage that reaches to supply voltage Vs, you will be observing this inductor have stored some energy with this polarity plus minus. And as this inductor have stored some energy, now that polarity of inductor will change. It will get minus plus, and this inductor will start to get discharge. And that discharging will give energy to capacitor. So capacitor will further charge up to some extent, you can see. But here this output current that will start to decrease and it will get to 0. And once this output current is reaching to 0, till this SCR is in on state, voltage across SCR will be 0. But once this output current, means a current passing through this SCR that reaches to 0, or one can say as if it goes below holding current, this SCR will get turned off over here. So you can see at this instant this SCR is getting turned off as this output current reaches to below holding current, right? As output current is similar to the current which is passing through SCR over here. And after that, this capacitor will start to discharge. You can see, so capacitor is getting discharged, and this output current will reaches to 0 as this SCR is off, and the voltage across SCR that will start to increase and it will reaches to plus Vs, right? So over here voltage across this SCR that is plus Vs as it is off. So that is how we are turning off this SCR. And now again, as if you give gate pulse to this SCR, it will get turned on. So here turning off operation of this SCR is getting done by out load elements LNC. That's why this method is even referred as load commutation method. I hope that you have understood this. Thank you so much.
So now we can watch the YouTube video for class A commutation. Now we have learned in this class what is thyristor commutation, what are the different commutation techniques, and the circuit and working of class A commutation techniques or load commutation. So here we have the few quiz questions and a few frequently asked questions. So next class we are going to discuss about the class B commutation. Thank you.